So I'll be talking about some recent works of ours on provably learning neural networks. This is based on, this talk is primarily two parts. One is going to be on upper bounds. This is joint work with Zhehao, Serbi, is this pointer working? Oh, there it is. Yeah, Zhehao, Serbi, Adam, and Raghu. I'll spend most of the time on the upper bounds. Near the end of the talk, I'll talk a bit about this other work that's joint with Arvind and Adam Raghu on proving lower bounds for this problem. OK, so I'm going to dive straight into the question because I think this is a setup that's familiar with many people in this audience. All right, so we're interested in pack learning, and we're going to work with sort of the simplest possible neural networks you could imagine. OK, so our object of interest is this linear combination of ReLUs of linear functions of the input. OK, so lambda i's are some mixing coefficients. Wi's are some weight vectors. Think of these as sort of the input layer of the network. And our goal is to learn this function from training examples. Okay, so we're given a bunch of IID XY pairs where the x's are sampled from some data distribution Q, and the y's are the value of the function at that particular x plus some mean zero stochastic noise. And in this talk, we're going to focus on sort of the canonical setting for this problem where the data distribution is just standard Gaussian. Okay? So to sort of steal maybe it's Lil's terminology from yesterday, I really think that this is like a nice sort of model organism for understanding non-convex regression in continuous domains. And of course, the goal is to output some function using these training examples, which is close to the true function f in square loss with respect to this data distribution Q. Okay? And the error parameter of interest is going to be this epsilon. Okay? Right, so of course, we don't see two-layer networks in the wild. We don't really see Gaussian data in the real world. But I would still argue that this problem has been a really rich testbed for developing interesting algorithms and analysis for non-convex optimization, methods for tensor decomposition, polynomial regression, representation learning, and dimensionality reduction. And even on the lower bound side, it's, as we'll see near the end of the talk, it's given rise to some pretty interesting gadgets for reasoning about the complexity of supervised learning, even over sort of continuous domains. Okay, and so people often say we don't really have any theory for understanding how deep learning works. Actually, the state of affairs is pretty embarrassing. Even for this very simple problem, it's still open whether you can do this in polynomial and all parameters. Okay, and this isn't just about analyzing gradient descent. This is really a question about any polynomial time algorithm. Right, so this is sort of the focus of this talk, or at least the first half of this talk. So I haven't, yeah.
Do you count like a statistical query lower bound as closing that open question, or
yeah, I would be happy with this lower bound. Yes, yes.
Okay.
I'd be happier if there were a cryptographic lower bound, but yeah.
Sure.
Yep. OK, so I haven't really told you about the scaling for this. So currently, as stated, at least formally, this goal doesn't really make sense. So let me impose some sort of standard scaling assumptions. So I'm going to assume that the wi's, these weight vectors, are of unit norm. This is without loss of generality because if these aren't unit vectors, you can always normalize them and push the factor into this coefficient here because the ReLU is positive homogeneous. Okay, and then the main scaling assumption I'm going to make is that these lambda i's, I can't assume that I can't just work with arbitrary unbounded lambda i's. So I'm going to assume that the sum of the absolute values of these lambdas is at most some parameter. Let's call it r. Okay, and so really, if you want this question to be to make sense in a scaling invariant fashion, instead of getting a polynomial, no, this is not working. If you want to get polynomial dependence on 1 over epsilon, really what you should ask for is polynomial dependence on r over epsilon. All right, so this is the question that we'll focus on. All right, so let me tell you a bit about what's known. There have been way too many works to fit into a slide deck on this problem, so I'm just going to focus on maybe like 3 or 4 results. And so apologies in advance if I omitted your paper. One of the earliest works on this noticed this nice connection to tensor decomposition, a topic that's of interest to this audience. So the general idea is as follows. So it turns out that you can get access to the following tensor, which is the linear combination of tensor powers of the weight vectors. And how you get this is by looking at the correlation between the y value, f of x, and some particular tensor valued function of x, which sometimes people call the Hermite tensor or the score, the score function. This is just some explicit tensor that you can write down. And you can estimate the left-hand side just empirically using examples. Okay? And at the end of the day, you get some noisy estimate of this low-rank tensor here. And some early works noted that if the weight vectors are well conditioned in the sense that they're robustly linear independent in some sense, then you can just use off-the-shelf tensor decomposition algorithms and get an algorithm that runs in fully polynomial time. Okay? There's also this nice recent work of Awasthi, Vijayaraghavan, and Tong that shows that even if the WIs themselves are not well conditioned, but let's say some tensor powers of these WIs are well conditioned, and this holds, for instance, in various smooth complexity settings, you can also get this kind of guarantee. Okay? Yep. Oh. The only, yeah, so for this Gensman et al., I mean, you would need, for instance, that K is at most D in order to even have a hope for it to be well conditioned. This Awasthi et al. Paper extends this to the overparameterized setting where K could be larger than D, but you still need some kind of condition number bound on the tensor powers of the WIs. Yep. Yeah, it depends. I mean, all this, if you ask for the tensor powers to be well conditioned, you'll get poly sub L. So there will be some implicit dependence on L. Great. Okay, so this is, I mean, so I guess the main takeaway from this slide should be that there's this nice object that's connected to this function. So this is this sort of fundamental connection between tensor decomposition and learning shallow neural networks that we're going to heavily exploit later in this talk. Okay, so now you could ask, if instead of imposing some structural assumptions on the weight vectors, what if I impose some assumptions on the output weights, these lambda i's? And so this beautiful work of Diaconicus and Kane showed that if these mixing weights are all positive, there's actually not a fully polynomial time algorithm, but at least some quasi-polynomial time algorithm based on some crazy, constructing some crazy net over some algebraic variety. But at the end of the day, it also crucially exploits this tensor, this moment tensor here. Okay? And now you can ask, if I make no such assumptions on lambda i's or wi's, what do I get? You get something. So under no assumptions, you can actually recover some function that approximates f in time, which is polynomial in the ambient dimension, but unfortunately exponential in all other parameters. Okay, so in particular, if k and epsilon are constant order, this is a polynomial time algorithm. But the really sad thing is that even if, let's say, the network is of constant size, and I wanted to learn to maybe error 1 over poly d, this is going to take exponential time in samples. One nice thing about this algorithm, however, is that it actually extends to deeper networks. But in this talk, we're going to focus really on the 2-layer setting. Okay, so this is the central question. This is the baby version of this open question I stated at the beginning. Even if I assume the network is narrow, there are only a constant number of neurons. There's no algorithm that gets polynomial in D and 1 over epsilon, and this will be the goal of this talk. So I'm going to tell you an algorithm that works for worst case 2-layer networks that achieves this guarantee. This is this first work that I mentioned. Okay, so we show that if the network is of constant size, you can get a poly D and 1 over epsilon time algorithm. Okay, more quantitatively, what do you get? Well, if the network is of size k, we get some exponential and quasi-poly in the size of the network. For the kinds of techniques that we use, we expect really the right answer to be d to the k. And so this is a nice open question. Yeah.
Why did the previous result get exponential and 1 over epsilon? Because based on what you said, okay, yep. I learned the span of the w's. Now I have a subspace. Yep. Now I would imagine doing brute force search in the subspace with an epsilon net.
Yes, yes. And that part is fine. Yeah, yeah.
Okay, so because the number of the points in the epsilon net would
is 1 over epsilon to the number of, yeah, exactly. Yeah, so the issue is really finding the span. So unfortunately, this PCA approach that I mentioned, you need to cut up the data in various ways, and you kind of need to wait for, for instance, a label to get really large. So you have to kind of wait out in the tails for a long time, and as a result, you pay this exponential and 1 over epsilon.
So it's a samples thing.
Exactly.
I'm waiting for a
exactly.
rare type of sample.
Yep, yep, yep. Okay, so this is the result I'll tell you about. I should note that in some sense this guarantee actually extends to any reasonable activation function, not just ReLU. As I mentioned at the beginning, we can handle any kind of stochastic mean zero noise in the labels. Okay, and so even if you don't care about neural networks, I hope the algorithm is of interest because it's ultimately a question about tensor decomposition, where actually instead of decomposing a fixed tensor at some single degree, we're going to cook up some tensor decomposition question at multiple degrees, and somehow we're going to get out a recovery guarantee even in the absence of any kind of condition number bound, like typical tensor decomposition algorithms. Okay, so here's sort of a first attempt. This attempt is horribly wrong, but it gives some intuition for the general approach. Let's assume for starters that we actually have exact access to these moment tensors, these T sub L's, which are just linear combinations of tensor powers of the weight vectors. Okay. Let's even start from the beginning. So let's imagine we have access to T sub 2. And this is nothing more than a linear combination of projectors to the weight vectors. Okay? And so you might think, like, well, this is some linear combination of projectors. Surely if I take the top k-singular subspace of this is going to give me some information about the span of the weight vectors. And so if you haven't seen this before, the surprise is that if I don't constrain the lambda i's to be positive, then you can actually cook up crazy cancellations, and this matrix can actually be 0. Okay? So in worst case examples, you can't get any information out of just degree 2 moments. Okay? Well, you could ask, what about higher degree moments? And this nice construction due to Diakonikos et al. Also, relevant work is this work of Serbian and folks, shows that there exists some choice of parameters such that actually all of the moment tensors up to some degree that's scaling linearly in the size of the network vanish. So what is this saying? This is saying if I only use sort of degree k polynomials or below, I can potentially get literally 0 information about the underlying network, at least in the worst case. Okay, so this seems like bad news. And this is also kind of intuition for why you would expect that these kinds of tensor-based algorithms need maybe a d to the k dependence in the runtime. Okay, but how do we get around this? This isn't so bad. It turns out if I just look at moments of degree at most k plus 1, I'm already in good shape. So here's an argument for this. So I'm going to take this tensor, and I'm going to construct some matrix out of it by contracting along some random directions. So I'll sample some Gaussian vector g, and I'll form some matrix. It's not super important if you haven't seen this notation, what this means. But at the end of the day, you can get access to the following matrix. So it looks very similar to what we saw before. You have this linear combination of projectors to the weight vectors. But now you have this extra factor, some power of an inner product between your projection vector and your weight vectors. And now the hope is if I take this and I vary L from 2 all the way up to some high enough degree, I'm going to get access to a bunch of different kinds of linear combinations of the projectors. And hopefully that space of different linear combinations will be enough to actually extract out interesting information about the tensor. Okay? And so let's see this concretely. So if I look at L equals 2, this is just what we saw before. In this case, these prefactors, G inner product Wi raised to the 2 minus 2, that's just a bunch of 1s. Okay, so this is a vector of k 1s. If I look at L equals 3, now the exponent is 1, so I get a vector of inner products. And if I go all the way up to L equals k plus 1, I get a vector of powers of inner products. Okay, this is some k by k matrix. This is nothing more than a Vandermonde matrix, right? So if the Wi's are all distinct, with probability 1, these inner products are also going to be distinct. And Vandermonde matrices with distinct nodes are full rank. So this seems good. This is saying that somehow if I look at the range of different linear combinations I can get out by varying the degree, once I go up to degree k plus 1, I actually see sort of all possible linear combinations. Okay? Now, of course, there's this annoying lambda that we have here, so let's just stick in the lambdas as well so that this is the full coefficient for, like each of these entries corresponds to one of these coefficients. Okay? If the lambdas are non-zero, this is fine. This is still going to be full rank because you're just multiplying by some non-zero diagonal matrix. Okay, so this is nice, yeah.
If I had fixed L to be 2 and taken a bunch of different random contractions, like sample G and the G prime and G double prime and so on,
yep.
I also would have gotten a bunch of.
Yeah. The issue is that I think the issue is that let's say I do it for L equals 3, just because the matrix there, yeah. In that case, because the entire tensor is 0, if I contract, no matter how I contract, it's still going to be 0.
Okay, so you have to go all the way up to the.
So T3 will be 0 for these worst case instances. So regardless of what G I pick.
Fine, I'll do it. I'll start at I'll use L equals k plus 1 or something.
Yep.
But then instead of varying L, I'll just do a bunch of different contractions.
Yeah, that could also potentially work. Yes. That could also potentially work. This Vandermonde structure is kind of nice for what I'll talk about, but yeah, this could potentially also give you enough directions. Yep. Okay, so what this is really saying, to summarize, is that each of these gives me some different linear combination of the Wi transposes. Yep.
I think I lost something.
Yes.
Can you go back? That's not representing that sum, right? The matrix below. What is this matrix actually representing?
So each row vector is like a vector of coefficients for a linear combination of the WIs that you could achieve.
Oh, so the point is that like knowing that will be enough to
Yeah, so somehow like I want to say this matrix is full rank, and this is good because it says what are the kinds of linear combinations I can achieve by varying L. I can achieve this entire k-dimensional space, like the full space of possible linear combinations.
And if you
Yeah.
knew the matrix coefficients, then you could solve a linear system to get the WI transposes.
Yeah, that's true. That's true. Yeah,
But
yeah.
you don't know
But you don't know the matrix. Yeah, yeah, yeah. Exactly. Yeah. Yeah. So this matrix, it doesn't really exist. It exists in our heads. It's not something that the algorithm will work with, but it's kind of ensures that there exists at least some linear combination that will do the trick. In particular, if I look at these matrices, okay, I get all possible linear combinations of these projectors. What's an example of something in this space? Well, just the singletons themselves. Like, so these WI transposes obviously lie in the span of all WI transposes. And so there is some linear combination of these different matrices that's going to be equal to any single WI transpose. This is great news because K here is order 1, so we might as well just guess what these linear combinations are, and then we can validate our guess on held out test data. Okay? Yeah.
schema and the WI transpose are important, or I mean, could it not also the WIs directly?
Exactly. Yes. 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 Yeah. So this will be useful like later in the algorithm. Hopefully, I'll have time to talk about that. Okay. So how am I doing on time? Oh, geez. All right. So let me tell you about some stuff that goes wrong with this approach. Okay. So just to recap, in principle, we should have access to this whole space of linear combinations of projectors. But in order to like guess what these linear combinations are, I have to do some kind of brute force, and then I have to specify what is the space of coefficients I'm brute forcing over. And so the space had better have some a priori bound that doesn't depend on the WIs themselves. It should only depend on the problem-specific parameters of d, k, epsilon, and r. Okay, so we need some a priori bound on the coefficients of these linear combinations, but we don't have that because this kind of bound, it's only reasonable if this matrix is well conditioned to begin with. So it seems like we're back to square one. Like somehow we still need some kind of condition number bound in order to get a reasonable algorithm based on tensor decomposition. So what are ways in which this could become ill-conditioned? One problem could be that some of the mixing weights are just close to 0. Right? So if I have some mixing weight that's close to 0, the corresponding column is going to be close to 0. That's obviously going to lead to an ill-conditioned matrix. But morally, this is fine because if a mixing weight is small, that means the corresponding ReLU isn't really contributing too much to this network. I might as well ignore it. Okay? The other issue is that I could have two nodes of this van der Waals matrix which are very close together. Right? In that case, the van der Waals matrix condition number is really dictated by the separations between the nodes. If they're close together, all bets are off. But again, this seems like it should be fine. Okay, and here I'm going to kind of conflate inner products being close together and the actual vectors being close together. These are related up to poly D factors with high probability. Okay, but intuitively, if I have two weight vectors that are really close together, I might as well treat them as the same weight vector. I might as well clump them together into a single ReLU and try to estimate that ReLU in the overall network. Okay, so if two weight vectors are too close, there's no real need to distinguish between them. At least that's what you would think. Okay, so one of these two issues is fine. The first, you can sort of really ignore the role of small lambdas. But it turns out the second issue is actually quite delicate. Okay, so I want to spend a bit of time on this. Okay, so here's the sort of cruel quantitative twist. So first of all, let me ignore the lambdas for now. Just think of lambdas as plus minus ones. Okay, so what we do know is that if these numbers are all separated, if they're all spaced apart by some margin of delta, the condition number of this is going to be pretty good. It's going to be 1 over delta to the k. Okay? Now, if they're not very well separated, if only like some clusters of neurons are well separated, you could say, well, I'll just take all these different clusters and maybe I'll just clump them together. Right? And now I have a well separated instance. Right? Now the condition number is actually good if I pick delta carefully. But here's the issue. By clumping things together, I've moved all of my neurons by a distance of roughly delta, which means I've perturbed this moment tensor T sub L potentially by a margin of delta, maybe in like the Frobenius norm or something. Right? And so this is the key issue, because now you've introduced some extra error on top of your sampling error. I think it's just out of battery. And this sampling error delta is actually, this additional error delta is actually being blown up by the condition number. And no matter how you choose delta, this extra error you're incurring is going to be bounded away from 0. And so one way of thinking about this is that the win that comes from doing this clumping to improve the condition number is always swamped by the loss from perturbing the moments. Okay? So this is sort of the key subtlety. And so now let me tell you like a sketch of how to get around this. Let me see if I'm doing it on time. Okay. Right. So here's the workaround. Right now things are a bit coarse-grained. We're kind of splitting up neurons separations into 2 buckets. Like some neurons are less than delta separated, some are greater than delta separated. But it would be great if we had a more fine-grained understanding of the difference between these two, the gap between these 2 quantities. So if we had a much nicer picture like the following, where within a clump, actually neurons are really closely spaced, and between clumps, they're very far apart, then we'd be in good shape. If the radius of any clump were actually of order delta to the k, then this issue on the previous slide wouldn't manifest. So in other words, if the neurons within each clump were sufficiently tightly spaced relative to the distance between clumps, then we're fine. So ideally, we'd like to show that at some choice of scale delta, we have this nice clustering structure. And in principle, this delta must exist, because let's imagine I just take delta small enough that the clumps are actually just individual neurons. In this case, this clustering sort of vacuously holds, and I'm happy. But the issue is we don't have any kind of a priori bound on how closely spaced the neurons are to begin with. We want some kind of choice of delta that's only dependent, again, on the problem parameters d, k, epsilon, and r. So a very simple lemma you can show is actually such a scale exists. I won't tell you the proof, but this is where this kind of embarrassing tower scaling shows up. So what you can show is that there is some scale, roughly speaking, at epsilon to the k, at which you have this nice clustering structure. If this doesn't happen, then you can argue that the neurons are actually all epsilon close, and you might as well just clump everything into one single clump. So this is really saying that there exists some scale, delta, at which you do have this nice clustering structure. Okay, so this basically already gives, yeah.
Yeah, just want to make sure I'm understanding this right.
Yeah.
The idea kind of like, let's look at the largest gap. That gap, let's say, is like 1 over k.
Yep.
Then you look at like the second largest gap, the third largest gap, and so on. And unless either like the first largest gap is close to the second largest gap, and so on.
Yep.
Or there's like some point where there's a massive break, and then you
Exactly.
Or if there was no massive break, then even the smallest gap must be at least like 1 over k.
Exactly. Yeah. That's exactly right. Yep. Okay, awesome. So actually, most of the work in the paper goes in improving this doubly exponential dependence on k to something slightly less embarrassing. So let me tell you briefly what this entails. So previously, this was kind of overkill. We're insisting on this really strong clustering property where every clump is, there's this big gap between the size of the radius of every clump and the distance between clumps. But what if I just want to learn, one clump at a time? It turns out that if I just want to learn one clump at a time, I can ask for something much more benign, where I just need that clump itself is very closely spaced, and every point in that clump is far from every other point. But I don't really care what happens outside of this clump. It turns out that with this kind of trick, you can actually go down to much more reasonable scale, well, slightly more reasonable scales. Instead of epsilon to the k, you get something that's more like epsilon to the k to the log k, and this is where this d to the quasi-poly k dependence that we get comes from. Okay, so that's all I wanted to say about the upper bound. Okay, this is maybe a poor decision. So let me talk briefly about the lower bounds, and I'll conclude with, I want to spend some time on the open problems. Okay, so for the lower bounds, we're actually, it's still open whether you can, learn 2-layer networks in polynomial time. So let's make our lives as lower bound people a bit easier. We're going to work with not 2-layer networks, but 3-layer networks. So a 3-layer network really is just you add an extra sort of nonlinear layer of ReLUs. And so now instead of one set of weight vectors W, you have 2 sets of weight vectors. That's the only difference. Turns out I still don't really know how to prove lower bounds for this setup, so let me make my life even easier. Let's imagine I actually have some added bias terms, right? Let's imagine that at every layer, in addition to doing this matrix vector multiply, I also add some vector of biases to the activations. Okay, so what's known about this setting? A very nice work of Daniele and Vardi in 21 showed that for this problem, actually, there is a computational lower bound if you believe some particular crypto assumption like the existence of local PRGs. But more precisely, their lower bound applies not to such functions, but to ReLUs of such functions. This is a somewhat minor point. So I want to say briefly like how their reduction works, because this is it's a very nice sort of gadget reduction that might have use elsewhere. So at a high level, the issue with working with showing lower bounds for supervised learning over Gaussian inputs is really that Gaussian inputs there's a lot of information encoded in these vectors. Whereas if I work with, say, Boolean inputs, it's much easier to cook up hardness results. Okay. Okay, so our starting point will be, I know it's very easy to show that these neural networks are hard to learn when I only get Boolean examples. How do I somehow lift this to the continuous domain? Okay, so one dumb way of doing this lifting is just to say, well, if I have some function f, which is hard to learn over Boolean inputs, then obviously f of sine of the input is going to be hard over Gaussian inputs, because the sine function is going to completely erase any scalar information about the inputs, and you're only going to preserve whether or not an input coordinate is positive or negative. Okay, and then you could say, well, okay, the sine function is discontinuous, so you can't really implement it with ReLUs that are of, say, polynomial norm. But what you can do is say, okay, like I'll just approximate this by some kind of ramp function, and I'll take the slope of this ramp function to be some huge polynomial. Hopefully that will still be fine. Okay, and so the key issue here is that because you have this annoying like inverse poly width region where the ramp function disagrees with the sine function, this reduction could potentially leak a lot of information about the underlying function whenever you see examples that fall within this dangerous region. And so the key workaround that Daniele Vardi introduced was to define some new network based on this penalty network P. Okay, at a high level, the reduction is some new neural network that isn't just f of ramp of x. You subtract out some penalty term that allows this function to go to 0 whenever you're in this kind of dangerous region where you might leak information. So whenever the inputs actually occupy the region where ramp disagrees with sine, the function is actually giving you just a 0 label, and you're not leaking any information in that case. So this is the key gadget reduction. Sorry, it's a bit fast, but anyways, this is just to give you a flavor of the lifting. And at this point, you note that this function can actually be simulated as a ReLU of a 3-layer neural network, and then things work out. Okay, so this is the general lifting procedure. In this this work with Arvind, Adam, and Raghu, we refined this lifting procedure to get rid of the ReLU on the outside. But my favorite aspect of this lower bound is actually we managed to extend this beyond just cryptographic hardness, but actually hardness in SQ, which is a bit surprising because there is some conventional wisdom in the literature that for these kinds of real-valued regression problems, somehow you can't hope to prove SQ lower bounds. The key workaround in our setting is that the kinds of functions that we show are hard are almost Boolean. And so the kinds of non-degeneracy assumptions that are needed in this no-go result of Impala et al. Don't apply actually to our instances. Okay? And then we also, in addition to SQ, we also show that this lifting extends to this membership query access, where instead of Gaussian examples, you can kind of query this function as a black box at any point you want. In this case, you have to use slightly larger neural networks, but you still get cryptographic hardness based on pseudorandom functions or something. Okay, let me also mention some very nice follow-up work due to Daniele, Cerebro, and Vardi, where by going up to slightly higher depth, they show that not only are worst-case neural networks hard to learn, but actually even smooth neural networks are hard to learn. So what does smooth here mean? I take an arbitrary neural network, and I slightly perturb every weight by some Gaussian of size roughly 1 over poly. And you might hope that in this kind of setting, just like in things like the analysis of the simplex algorithm, all of a sudden you can get polynomial time guarantees. And they show quite surprisingly that this is not the case if the smoothing is sufficiently small. Okay, and the takeaway from this result is really that I think we really need to think hard about what kinds of structural assumptions we need in order to go beyond these, first to go beyond 2-layer networks and also to circumvent these kinds of lower bounds. This is a very hard question. Open to discussing this with people in the audience because, yeah. Oh, things are all quite ill-conditioned. But to give a sense for the intuition for why this lower bound holds, in some sense, like because you're working with ReLUs, you have a lot of freedom to like zero out particular things, just like we saw in the lifting from the previous slide. And so they're kind of showing that even if you smooth the parameter slightly, the behavior of the function still kind of looks like the original worst case network. Okay, great. So let me just flash, I guess, the open problems because I'm out of time. Okay, so the natural question, at least in the context of the first half of this talk, is of course trying to get this d to the k instead of d to the quasi-poly k. I think this is the most concrete next direction. But in general, yeah, it's still a little embarrassing that we don't even have fully polynomial time algorithms, not just for general two-layer networks, but even in this case where the output weights are positive. Hopefully some recent progress on learning mixtures of Gaussians using essentially log k moments, but in polynomial time could be useful for this. There's also a question, we have lower bounds in the smooth complexity setting, but they really require the smoothing to be quite small as a polynomial in D. And the question is there some kind of phase transition? Because at one extreme, we have worst case networks, and if I really smooth them out at the limit, I just get completely random networks. And completely random networks admit various kernel-based approaches that allow you to get efficient guarantees. And the question is, at what point in the smoothing do you transition from hard to easy? I have no idea what the answer is. Yeah, some other technical questions, but I think really the main conceptual question, which seems very tricky, is really articulating reasonable distributional assumptions and assumptions on the underlying function for which that seem to match what we see in practice and for which we can get polynomial time guarantees. Again, this is sort of the grand challenge of this research direction. All right, so yeah, thanks for listening.